Welcome to the online causal inference seminar. Today, we're excited to have Luke Miratrix, who will talk about using national data and meta-analysis techniques to get a handle on how bad some biases might be in practice. In Q&A, we have Ben Whiteman, who is a collaborator of Luke and who's happy to answer your questions. Yeah, please put them there. We will also select some of them that will then be asked live. After the talk, we'll have a discussion by Beth Tipton, and after that, Luke will be able to respond. Thank you all for coming. As usual, today the questions will be handled by me. As I said before, please submit them in Q&A and we will select some of them to be answered live. I'm now switching over to Luke. Feel free to start whenever you're ready.
Great. Hello, everyone. Let me just set up my screen share here. So today I look forward to talking about some work that my student Ben Weidman has done. This crosses two different papers. So this talk is going to give some high-level structure, and then we're going to use that structure to investigate biases in two different places. This abstract is just, if you want the slides, they're posted online, and this is the abstract for the talk. So the driving questions of this work are sort of how bad does it get? So in matching type or quasi-experimental designs where you're trying to extract some sort of as-if randomized experiment from observational data, you might want to know, like, does matching on covariates really give us an as-if randomized experiment? And how much confounding is left? Is the bias that is left over due to unobserved confounders enough to really swamp our expedition? Similarly, in actual real-world randomized experiments, especially in places like education, people in good faith attempt to run randomized experiments, and then nobody cooperates or does what they're told. So you have things like attrition, where you lose people after you've randomized them. There's a lot of fear that attrition can really undermine the gold standard validity of a randomized experiment. We might want to know how much ruining happens. So to think about these biases, there's sort of three large bins of bias we might consider. One is who's in the sample. This boils down to external validity bias or generalizability. We can also ask, how is the treatment assigned? Was it actually assigned at random, or were people self-selecting? This is confounding or selection bias. And we can also ask, whose data did we analyze? Did we lose people along the way? This would be attrition bias or missing not at random, and other kinds of missingness mechanisms. And we can sort of put all of these bias categories in a table, and we can look at randomized trials, and we can look at matched trials as a comparison. And with randomized trials, they have some strengths and weaknesses, and matched or observational studies have other strengths and weaknesses. In particular, randomized trials, you have that randomization. Observational studies, you usually have more data. Now with observables, when you have observed confounders or problems, you can correct for those observables using various modeling and usually drive the biases down to small or basically zero. It's the unobservables where we really have to stress because we can't get a handle on them. So having some sense of how big they might be in practice can make us feel better or potentially worse about whatever activities we're up to. In this talk, we're looking first under the observational study literature. We're trying to get a handle on what kind of residual bias is left over after you try to repair an observational study with the observed variables. And you can get that down to small or medium, that's the prior literature, but the prior literature is also a little uncertain. So we're going to try to add to that prior literature by looking at a host of different studies to see if we can get a sharper handle on how bad it is. The second part of the talk is this more uncharted area of how much do unobservables impact attrition bias, and can we get a handle on that? The way we do this is using within study comparisons. Within study comparisons, the idea here is we know something, at least approximately, in some context where we somehow are given the real answer. And then we analyze the data as we normally would, not looking at that real answer. And we compare our method's answer to what the real answer is. And then we have to sit there and think about, well, there's uncertainty in both these activities. Usually the real answer is known with a certain amount of imprecision. Our actual answer, similarly, if they're really close, then we're like, wow, it worked. We've managed to replicate our gold standard. So whatever methods we're using, at least in this particular instance, work. But we're left with how close is close. Also, with a single case study, a single within study comparison, we just know it worked in this very specific context. If we really want to have faith that these tools work more broadly, then we would want to have a large body of within study comparisons so we can have a sense of how they tend to work. Also, by having lots of within study comparisons, we can look at how much they vary, and we can try to disaggregate the measurement error of estimating whether things worked or not from whether they actually are working in expectation. So we can try to say something a little more precise. So there's some key points. So if you have a good within study comparison, you're going to have that true target estimate that I mentioned. And you're also going to have this is what we really do estimate. And the difference is our estimate of bias. And now to get a handle on the uncertainty of that bias, we will take the standard errors for each part and use those standard errors to get a standard error for the difference. And that would be the uncertainty about our bias estimate. And then finally, within multiple within study comparisons, the way we're going to do that disaggregation I mentioned is stealing from the meta-analysis literature. We're going to think of each of the within study comparisons as its own study, and then look at how the point estimates of biases range across those studies, and estimate sort of how much structural variation there is in those point estimates, as opposed to how much variation there are due to the measurement error. So that's the stage, and now there's two acts. The first act is the wonderful world of matching, or quasi-experimental designs. And so that's, and the paper for this is recently been published. It's called Lurking Inferential Monsters, Quantifying Bias and Non-Experimental Evaluations of School Programs. I will point out that you'll notice that the title of this talk was not a particularly clever title. That's because I named it. But if you look closely, you'll find that the titles of both papers that this talk is about are very clever titles, and that's because my student named them. My student was not helpful in naming the talk after repeated attempts, so I was left on my own. I apologize for not being clever there. So, within study comparisons of matching, if you can imagine a within study comparison, we have this large target population. And in that large target population, there's this selection mechanism that, are you going to be in the experiment or not? And so that's S. So we have the study sample, and then we randomize the study sample into treatment and control. That's the T. So if we're looking here, this study sample is a subset of this larger target population. We have our treated units. They're impacted by whatever it is we're doing to our units. And due to randomization, we know that the distribution of the treated units potential outcomes under control is going to be the same as the control unit's potential outcome under control. So this comparison is our gold standard comparison. So that comparison is our target answer. And then what we're trying to say is, can we recover that using observational study methods? So ideally what we would do is we would take this treated group and we would construct a comparison group from the non-sampled units by finding non-sampled units that are similar to the treated units based on various covariates that we have at their disposal. And then we could compare these two things, and that would give us an observational study estimate, sort of. I'll get into that weeds of that in a little bit. And then the question is, does that observational study estimate echo the gold standard RCT estimate? So there's tau hat is our RCT. There's our non-RCT estimate. The bias in the observational study, because we're assuming our RCT is our gold standard, there's no bias there. So the bias is going to be the difference of these two estimates, which turns out to just be a contrast between the comparison groups. We don't actually need the treatment group at all. We can just focus on whether we can construct a comparison group that mimics the actual control group. So our estimated bias is the difference. That's basically just what I said. So characterizing that bias, now we can decompose the bias a little bit further. So we can talk about the adjusted mean comparison outcome, where you could imagine if we're fully adjusting for covariates, we can have this function here, the mu c control group function, which is the expected control potential outcome given observed covariate values x for the control units in the non-selected sample, the people that are set aside. And using that definition, then our adjusted control potential outcome would be the integral of that function over the distribution of the units in the treatments, the control group arm of our RCT. So you can think of our best case control potential outcome using our observed covariates is essentially a reweighting of the non-selected units to match the distribution of our RCT. And then if we do that, then we can decompose bias into two pieces. The delta U is the piece that's left over. That's the difference between our comparison group and, that's the difference between the control group in our RCT and our adjusted comparison group. So that's, if we do the best adjustment possible, we're left with delta U. And then the delta X is if we didn't do any kind of adjustment, if we just used all of the units in the non-selected group, that would be, and without adjustment, that would be sort of the bias that we can fix. Now, I'm going to go on a brief tangent, which is there's a very subtle aspect, or subtle to me anyway, of within study comparisons that I just want to highlight, which is what we want from a within study comparison is we want to know if we can recover an impact estimate in a true observational study, i.e. we want to know if we find control units just like treatment units who decided to get treatment on their own, are we going to get a real good estimate of a causal effect? But if you think about what we're doing with a within study comparison is we don't have any treatment units that self-selected into treatment. We have treatment units that self-selected into a randomized trial where they might get treatment, which is a different selection mechanism. So if the within study comparison is really going to test whether observational study methods work, well, we're not actually in a pure observational study domain. We're in a sister domain. So the mechanism, if the mechanism for deciding to enroll in an RCT is similar to the mechanism for deciding to start up a treatment program on one's own, then a within study comparison is meaningful. So, but really a within study comparison is an argument by analogy. Okay, so our context, a context which I now realize I've told you literally nothing about, we're going to find that RCTs, I'm going to tell you more about the context soon, but in our context, we feel pretty good. RCTs are a waitlist design, so the schools want the stuff. That's why they enrolled in the RCT. So there's some hunger for that. That mimics a situation where schools would adopt treatment on their own. Schools are paying some substantial cost, so it's not that the RCT makes everything free, so you get a bunch of schools that wouldn't normally take treatment if they were not given the extra bump of an RCT. So that feels fairly similar. And then we also did a few follow-ups, and we found that schools continued to use the RCT program after the evaluation. So again, it shows that there is a real commitment, similar to the kind of commitment you might expect for a school adopting a treatment on their own to fix some problem that they perceived they had. But I do want to just mark this important caveat. I think this caveat can be drawn out a lot more in much of the within study comparison literature. Here is a picture of the prior literature, and in the prior literature, we do see that within study comparison evidence there are some estimates out there, and it shows that we can correct. The biases tend to be relatively small. So let's turn to what we do. We have, or Ben has more accurately, access to basically all of the students in England in what's called the National Pupil Database. And in England, there's standardized tests throughout the entire country. So, and most of the students, basically virtually all of the students will sit for these tests. So we get to see these students at periodic points throughout their school lives. And we also are going to have this host of variables on these students and also variables on the schools and the context that these students live. So the other important thing is there are all of these RCTs that are being run in England, and those RCTs are randomizing, and these are schools being randomized into treatment and control. So we have essentially cluster randomized designs, but all of those RCTs are also in this database, which means that we have lists of students that are in the RCTs, and we can embed all of those RCTs in this larger context of all the students in England. So it's a perfect platform for conducting within study comparisons, because we have some small percentage of all of the students in England are in this selection of RCTs. We're going to use those. They were really randomized. Basically, everyone takes tests, so we don't have to worry about attrition and things like that. And then we're going to look for the exact or similar students elsewhere, and they all have the same outcomes because all the outcomes are standardized throughout the country. So in order to estimate selection bias, we're going to do two things. One is we're just going to have a naive bias estimate, which is sort of our benchmark. We're just going to take the RCT control and our observational control, namely all the rest of the students that are not in the RCT, and just see how big of a bias there, how big a selection bias issue might be. And then we're going to look at our actual, we're trying to do something estimate, which is we're going to do some matching. We're going to use one-to-one matching without replacement. We use Mulholland-Obis distance, propensity score caliper. We decided to deliberately use a method that's common in applied research rather than something more cutting edge, because we want to sort of see how do things work in practice. It's also computationally cheap, which helps with our inferential strategy, which I'm going to touch on in a bit. A little bit more in detail, beta match is a contrast between the RCT control and the matched comparison group. And we're going to just fit, so we do matching and then we do a regression adjustment step, and we fit a multi-level model with school effects and look at the result. And we're fitting to our two comparison groups. And what we hope is that our beta match is going to be 0, but if it's not 0, that would be an estimate of the bias in that particular context. We have a few outcomes for each intervention, and we have a collection of interventions, and we basically do this independently for each intervention and outcome. Our inferential strategy will take some of the correlation when we have multiple outcomes in a single intervention into account. I can talk about that later. Okay, so I'm going to briefly pause to see if there are any questions.
Thanks, Luke. I don't think there are questions yet, so I think you can continue and we take questions later.
Okay, great. So our bias estimates, this is the results of all of that work. The bias estimates are on the right-hand side, and then at the bottom here are just sort of box plots of the bias estimates for naive and for match. And we can see that the center of naive is, it looks like if we do nothing, then we're in trouble. The comparison groups in the actual randomized trials are much different than the rest of the country. But if we match on average, we seem to be right around 0, although we have these whiskers out, meaning that some of our estimates tend to be positive, some of our estimates tend to be negative. Which brings us to the next aspect of, are those estimates positive and negative due to random chance? Remember, we're estimating both our gold standard benchmark and we're estimating our observational study empirical estimate, and we would expect both those things to vary around their relative truths. So when we look at the difference, there's noise there. So even if we were perfectly matching in expectation and everything was hunky-dory, we would expect to see some scatter. So the way we're going to try to look through that scatter and get a sense of how much bias there is in general across all of our interventions and studies is to use meta-analysis. So meta-analysis is going to estimate the real magnitude of the bias. And the way meta-analysis works, we basically set up a model where we say, okay, our point estimate of bias, given the real estimate of bias, is, we'll just say normally distributed, which is not an insane assumption because we're essentially averaging over lots of things around that true bias and with some variance. And this thing we can actually directly estimate, and we're going to estimate it and then assume it's known. And then we have, this is, I like to think of it as sort of a Bayesian-ish in spirit assumption of we're saying that all of our point estimates or all of our true biases are normally distributed around some average overall bias and with some variance tau squared, which describes how much bias tends to occur across studies of this type. Now, what we really want, or the thing that I care most about, is that tau squared, because it's telling us even if on average bias is 0, that's not that comforting. It means that, say on average bias, if on average bias was 0 with that new, if there is some substantial variation, it means that some studies we would do our observational study and we just blow it and end up with a big positive bias. In other study, we blow it and there's a big negative bias. If those biases are not taken into account in any uncertainty estimation, then we're going to be generally making overconfident statements one way or the other and just be wrong a lot in either direction. So what we really want to know is, in general, do these observational studies methods work, i.e. is it controlling the bias? Even if the bias is on average 0, we want something more than that. We want the bias to be generally small, so we could just ignore it. We basically fit this multi-level model where we're assuming those sigma squared KWs are known. And then after, we can use that to get our estimates of tau and nu. And then we do empirical Bayes to shrink all of our raw estimates of bias. And then empirical Bayes tends to overshrink. So then we, for visualization and just discussion and presentation to make this these works accessible to more applied practitioners, we then immediately rescale them to match so that the variance of our individual bias estimates across our studies matches the variance, our overall estimated variance of the biases. So when we do all that, we get the following picture. So the top is the naive estimates. When we do nothing, this is our distribution. It's a very rough picture of the true distribution of biases across all of our studies and interventions. And then at the bottom half of the slide, we see the distribution of true biases across all of our interventions and studies once we've adjusted using all of our various covariates. And what we generally see is the biases after adjustment get to be fairly small. The standard deviation is missing on the slide, but it's around 0.03 or something like that. And there is some spread. So according to this picture, it's not entirely impossible to find biases on the order of 0.1 standard deviations or 0.1 effect size units, which would be a bad day, admittedly. But generally speaking, a lot of these observational studies seem to have biases that are relatively negligible, unless we're in some sort of nudge literature where we're looking at very, very small effects. So what does all this mean? Well, we compared RCT to matching in 42 times, and we didn't find systematic differences. The results were similar for math, reading, and writing outcomes. Some adjustment is necessary, however. Our unadjusted estimates, going back a slide, were negative and varied. So we had the systematic trend, meaning that the kinds of RCTs that we see are serving a specific kind of school. That's not entirely surprising. But if we naively just aren't comparing those students to carefully chosen students, then we will be blowing it to a fairly large degree. So given all of that, some may be tempted to conclude that selection bias isn't a big problem. So as long as we're working with school evaluations with a national pupil database, right, you can have all these caveats. We're examining a fairly specific scenario. We are in one country. We're looking at one kind of outcome. We're looking at school level interventions, et cetera, et cetera. Even all of that, we're a little bit cautious. We say that this may go too far, and there's some limitations to bear in mind. Non-radical interventions is what we're looking at here. The selection bias itself is a moving target. We want to keep rechecking it. This is more a call to arms that we need more of these within study comparisons in different contexts, which happily, as long as we have ways to link randomized trial information to larger databases, where you have some sort of standardized tests, you could replicate this kind of thing in all sorts of contexts. the more we do that, the more we'll get a sense of how well these things tend to work in practice. I've showed you sort of the applied takeaways, but in the paper itself, the way we do the inferential strategy to do the meta-analysis is we need to estimate these uncertainty estimates for the biases, and we need to take the correlation structure into account of the various outcomes. I encourage you to, if you're interested, to go look at the paper where we sort of spell out how to conduct meta-analysis in these ways, where we do a simulation style inference, where we assume that there's no bias and we can generate a simulation of what the distribution of biases look like, so we can have some sort of more rigorous testing as to what's going on. Anyway, some fun details there. All right, so that is the end of the first act, and then I'm going to basically say everything I just said over again, except replacing observational study with the word attrition. But before I do that, are there any questions, or should I just keep going?
There are some questions in Q&A. I think Ben is taking care of it. There's one by an anonymous attendee who asks, can you please explain again how the bias in each paper is calculated?
Yes. So the way we calculate bias is we have take a particular randomized trial. So there's one that I think it's called Chess in Schools. These very optimistic researchers wanted to teach chess to children, and that would cause them to be engaged with chess, school, and therefore do better on math, was, I believe, the working theory. So they did a randomized evaluation of chess in schools, where we have some number of schools enrolled in this study, and half of them got this intervention and the other half got the intervention later due to a waitlist design. So at the end of that, we have a collection of kids that received the intervention and didn't, and a collection of schools that received the intervention and didn't. Given that, we can compare them to get an estimate of the impact of chess in schools for that collection of schools. And then what we do to get an observational estimate, so that is our gold standard. And then for the observational estimate, we take the control schools, and for each control school, we try to find a matched school, a school that has similar characteristics along a whole host of measures, average test scores, neighborhood type, things like urban versus rural, things like that, region of the country, I think. And then we take the average outcome of all of those control school students and compare to our RCT control group. And the difference in those is our estimate of bias, is the estimate of selection bias. How different are our constructed control group from the actual? Something that I would like to highlight here is we can actually, in some cases, we're playing a little bit of a game where the primary outcome of some of these interventions might have been some kind of commercial test. And this will come up more with the attrition example, where, but we don't care, like whatever outcomes are being used, what we do is we use the national tests that all students throughout the country are receiving and use those as outcomes. And since we're looking at a selection bias, we argue that looking at these outcomes, even if they're not necessarily the primary outcomes that the researcher originally identified, is still okay in terms of testing the validity of the selection bias, because we're not so much interested, we're not actually interested in the treatment impact or whether the treatment worked or anything like that. We're just interested in whether we can recover control group like people using observational methods rather than relying on the randomization. And the way we test that is we look at these three standardized test scores as three different measures of how these groups may be different. All right. So let's talk about attrition. So here, I just want to call out, this paper is submitted, but it's not yet published, but we're happy to share it. It's currently posted on my lab group's website, so you can find it there. In an attrition context, we have an evaluation sample. So attrition is, you have a bunch of people that you've rounded up for your randomized experiment, you randomize them into treatment, and then you randomize others into control. And then after you've done all of that work, a bunch of people in your treatment group bail on you, and a bunch of people in the control group also bail on you. So at the end of the day, you only have your treatment responders and your control responders, the people that stuck around. And what you're going to probably do if you're ignoring attrition, which is what a lot of people really want to do, is you're going to compare this group to this group as your estimate of a causal effect. If you notice that there's attrition, you might adjust for baseline covariates. If you see that you have some difference in the baseline covariates, you could adjust your comparison of your treatment and control to repair that balance. This is moving an RCT more in the direction towards an observational study. So what we're going to do, because these randomized experiments are, again, part of this national pupil database and happening in England, is what we can do is we can say, okay, people ran these RCTs and they have their particular tests, this commercial test that they're using to estimate the impact of some intervention, but then they have people dropping out of the intervention and so on and so forth. So the evaluators were analyzing the responders, the treatment responders and the control responders, but we actually can look at the full range of all the student data, and we can find all the students that left, and we can include them, and we can do an analysis, which is the full treatment group, including the ones that were lost in the original evaluation and the full control group. Now, we can't, of course, do that with the commercial tests that were used as part of the original experiment. But again, we can turn to the state tests and we can estimate impacts on the state tests for the full sample as compared to the responder contrast. So that's the general idea. Before I do that, I just want to flag two different ways that attrition can hurt, which is another subtle point that was a surprise to me when we started to think about this more deeply. So I will share it. So we have a collection of units that we're going to randomize into treatment and control. And we can think of these units as just pairs of potential outcomes. We don't care about the underlying differences of the units. Randomization sort of solves that. So every unit, we see the blue numbers of the units treated, other number if it's in control. And if we imagine that they get randomized, and for the moment, just assume that they're randomized into perfect balance. If they're randomized in perfect balance, then we have this full estimate between the treatment and the control, and we get tau hat of 2.75, which is the average of all of the treated outcomes minus the average of all of the observed control outcomes for the control group. Now, oops, stop that, go back. So there's the first kind of attrition we might consider is nice attrition. We lose the same sorts of units from both treatment and control. Now, with that, we're still going to get an estimate of an average causal effect for the remaining responders, and it's a valid estimate, but that estimate might not generalize to a larger population. So here I deleted units that had a specifically large response to treatment. And if we have attriters, if the people that are particularly sensitive to treatment are dropping out of the study, then our overall estimate of treatment is going to be valid, but it's going to be not reflective of the full sample. It's going to be reflective of the remaining sample. So that's sort of the nice attrition. It's a generalizability issue. We also have differential attrition, where if people in the treated group are quitting for different reasons than people in the control group, then we can have systematic imbalance induced by attrition. And now our estimate of average treatment effect isn't really an average treatment effect estimate at all. It's biased. So there's sort of two mechanisms at play. One is attrition causing us to not be able to generalize to the full sample, but we still have a real randomized experiment? That's if attrition mechanism is sort of the same in both the groups. Or we can have attrition that's a much worse kind of attrition, which is differential attrition, where people in each group are quitting for different reasons, which creates imbalance in the group, so we no longer have a valid causal contrast. So we can dismantle attrition in these four components. So there's a lot of ways to sort of think about how to express attrition in pieces, but one way to do it boils down to, we can think of, here is our overall true average treatment effect for our full sample. And then here is the contrast which isn't really an average treatment effect if there's differential attrition, but it's the expected value of Y1 of the people that stay in the treated group minus the expected value of Y0 for those who stay in the control group. We can rearrange that to get this expression, which sort of boils down to 4 pieces. The PT and PC, those are our rates of attrition, like 10, 20, whatever percent. And the delta T and the delta C, which are the things that we don't necessarily know, is the difference of the treatment attriters versus the treatment group, full group, and the difference of the control attriters versus the control group. Sorry, the treatment responders versus the treatment group, and the control responders versus the control group. What we're going to do, so I'm going to stop there. Any questions, or should I keep going?
There were some questions, but Ben is taking care of them. So
all right,
you can
thank you, Ben, for saving me from having to embarrass myself. Appreciate that. So onwards. So what does attrition really look like? What we're going to do is we went back to this large database and we identified 10 RCT trials that were subject to attrition for some commercial test that they were originally interested in. And then we're going to identify which outcome is closest to whatever the commercial test they were doing. For example, if the commercial test was they wanted to know if the kids learned any math, we're going to use the math test. And then we're going to analyze the trial using the full sample and then the responder sample. And our attrition bias is just the impact in the full sample minus the impact in the responder sample. First, the rates of attrition across the 10 studies that we identified, we saw about 19% on average, but that's driven by there's an outlier of the Mind the Gap study, and then generally other studies had attrition of below 20%. And if you look at the treatment versus control, there's some areas where there might be some amount of differential attrition, but usually at least the overall rates of attrition is about balanced. Of course, you could have very bad differential attrition if 10% of your high achievers dropped out of treatment and 10% of your low achievers dropped out of control or something like that. So just having the same rates of attrition doesn't necessarily mean that you don't have a differential attrition problem. The main empirical results, this is basically using the exact same game and tools as the first part, is what we see here, which is we found that attrition ranged from almost negative 0.04 in effect size units to a little above 0.02 in effect size units, i.e., despite a lot of serious alarm bells that are constantly being rung about the dangers of attrition in all sorts of things like the What Works Clearinghouse and things like that, when we actually went and looked in these particular collection of studies, we didn't really see evidence that attrition was the huge catastrophe that one might think. We then further decomposed the mechanism using that equation I showed you before to estimate our delta T and our delta C. We have at the top, again, if we don't even bother adjusting for covariates, and then at the bottom, if we do adjust for covariates, we see that adjusting for covariates helps, but even if we don't adjust for covariates, what we're seeing is the attrition mechanism for the treatment and the control seems to be a similar shift. So the attrition, whatever is attrition is happening, tends to, if you will, cancel out, which is why overall we're not seeing massive impacts on the average treatment effects. We can use this mechanism to do one more little trick, which I'm going to talk about before I wrap up the talk, which is what we can do is we can use what we've seen in the literature, like this collection of 10 studies, to conduct a sensitivity analysis on a new study by basically saying, okay, if this is the kind of delta X or delta T and delta C we tend to see in practice, let's take some worst case ends of those ranges and see what that means for our particular study. We know how much attrition a given study has, and we can say, given that amount of attrition, we can plug those values into that equation I showed you to estimate how much attrition bias there was. So there's an intervention, it's a reading intervention called the REACH intervention. It's a waitlist design. The original estimates was fairly large, with 0.33 in effect size units with a standard error of about 0.1. And it had pretty high levels of attrition, 27% in the treatment group and 32% in the control group. So the question is, okay, so we have this promising study with a large impact. To what extent should we just be like, forget it, this is high levels of attrition, this study has been compromised, we can no longer consider it as a piece of good evidence? So the first thing we can do is we can do a sensitivity check where we plug different values of delta C and delta T into the equation from before and explore a range from no attrition, which gives us, this is our original estimate, to under what the worst observed case of attrition that we saw across all of our prior studies when we were able to sort of peek under the hood, reduces our impact estimate, but it still is quite hefty at above 0.2. So this kind of sensitivity check, I think mainly what it's going to do is it's going to illustrate that things have to be pretty bad. Mother Nature has to be pretty angry at you for attrition to really undermine your results in a substantive way. There's one other small trick you can do. Instead of doing a sensitivity check, you can actually just add the attrition bias. Think of the attrition bias as a random draw. So you have a new study, the REACH study, and we can think of Mother Nature as sort of drawing a random pull of what the attrition bias or what the attrition mechanism looks like from this distribution of attrition mechanisms. We can then, if we understand what that randomness looks like, we can add that randomness into the standard error. In particular, we can update our standard error to our old standard error plus our extra attrition noise. And the way we estimate that is we use this same equation, but we just plug in the variance. Sorry, we have our observed. First, we have our observed attrition that we can just see it in our data, and then from our prior studies, we have estimates of these two quantities, and now we have this, the variance, if you will, of the attrition bias, if we think of that as a random quantity. If we do that in this particular case, our confidence intervals sort of grow by about 12%. And we can also do sort of a variance decomposition and look at the fraction of this over overall variance and see that attrition is about 20% of our overall squared error, which gives us a sense of how big is attrition as a concern relative to all the other sources of uncertainty. Now, this as the tangent, I'm sort of interested in carrying this a little bit further to thinking about when we think about studies, if we have some even rough sense of where all of the pieces of uncertainty are, we could in general think about any particular study of like, where might we have gone most wrong in terms of our looking at our final estimate compared to what the truth is, which we don't know. Can we break that down into, it's 20% this, 20% that, 30% that, is potentially something to reflect on. So summary of our attrition research, we estimated attrition bias for 10 studies and 22 outcomes. The biases appear to be small. There's some evidence that kids in schools who drop are systematically different from those who stay. In particular, low attainers are more likely to leave treatment arms. But overall, it doesn't seem to be a big threat. I think that this investigation makes me think that a lot of the concerns about attrition are maybe a little bit overstated and we should be sweating about other things instead. All right, so thinking back across both these examples, we basically were in the game of finding data sets that had multiple RCTs in a similar domain. So we can sort of do a nicely motivated meta-analysis of a bunch of within study comparisons. I think the tools we've used these tools in sort of two areas and they have a little bit of different aspects in each of the areas, but the overall idea is roughly the same. We're using sort of bootstrap permutation resampling methods to get at inference, to estimate sort of the components of our meta-analysis. You can see the supplements for details on this. In truth, I think this is not really a truly frequentist evaluation. In this case, I feel more Bayesian in sort of how I think about these results in a more pragmatic way of sort of saying, okay, here's a particular context, given what we've seen within study comparisons, how bad do we think things are? We can think of that as, if you will, a random quantity, but I'll stop there. So any final questions, or we can just turn to Beth's remarks, which I'm looking forward to.
Thanks, Luke. I'll just read perhaps one quick one. There's a question by Jiaming Zhang, who asks, have you considered how these techniques for measuring and quantifying bias and attrition can be applied for a hazard ratio outcome instead of an average treatment effect?
No, that's a really good question. I think all of our tools, as long as you can estimate hazard ratios in a within study comparison kind of context, then if you can get point estimates and standard errors for each of your within study comparisons, then everything else we do sort of naturally follows. So I think that it shouldn't matter much under the hood, like what your data analytic strategy is. It really is, can you find contexts where you sort of have the full range of data and have your limited range? Now, if you're looking, and so you could extend this to cases where you had different amounts of follow-up data and different levels of censoring. That would be a really interesting direction in a lot of context, I can imagine. Thanks for the question.
Thanks.
Here, I'll stop sharing. Beth?
All right. Yeah. Thank you so much, Luke, for the very nice talk. We're now switching over to discussion. So we have Beth present some slides, and after that, Luke can respond. So I'm now switching over to Beth.
Hi, thank you. Can you guys see my slides? Very good. Okay. I guess I can hold on. Move this. Okay. My slides do not look pretty like Luke's, so they are just a nice, boring white background. The way that I sort of have thought about, and reading these papers, first of all, they're great papers, and I really enjoyed sort of, first of all, the data set that you have, which I think is remarkable, and the ability to answer, to look at these questions of a broad range of studies. What I was most interested in doing here is trying to think kind of to play devil's advocate a bit, I think, to think like the conclusions here are very optimistic. And so I've been trying to think through, are there other angles at which to get, to think about the results and how optimistic we should be from these results. So I don't probably have a full 10 minutes of comments, but the first paper on confounder bias, I was thinking about this range of bias being, once adjusted, is about 0.1 standard deviations plus or minus. And then that started making me think about what the average treatment effects might be in these studies, and how, is this, and how relevant this is to that. So could you think of these as a ratio, for example, for each? So if you knew what the estimate of the treatment impact was in a study, and you also knew what the bias estimate was in that study, I think that would be an interesting thing to meta-analyze. Or even just separately to know what the average treatment effects were, just to be able to say, is this bias large or small? I'm thinking in a lot of educational intervention studies, people power the studies for a 0.2 effect. But I feel like there's been recent work, often actually maybe also coming out of the EEF, that shows that effect sizes in these studies have been rather small, like closer on average to 0.06 or 0.09, in which case what we're showing here is that confounder bias could be as large as the average treatment effect in the studies. The second thought I had was about the covariate set. So I was looking through the covariate sets, and I was thinking, oh, I'm so jealous of a country that has a sort of standardized, well, everything really at a national scale, in the sense that this covariate set could include student achievement aggregated to the schools. And that's the variable that in the US system we're lacking at the national level, where we have that at state or in various states, but not at the national level. And so I was wondering if you were to redo the analysis without test score data, how well the bias reduction methods would perform. I think that's really important in other contexts. Okay. There's a little puzzle though in the first paper too that I'm not really sure what to make of, and that is that the bias that you're seeing here is that the treatment effects in the QEDs were actually the treatment effects are larger. Oh, my concern is that treatment effects are typically larger in QEDs than RCTs. And that's, we're usually worried that QEDs are overstating what the true causal effect is. But in this study, actually, it looks like they're smaller. In fact, that they're usually closer to like they're even before adjustment, they're smaller. And so I was trying to think about why that is. Why are they different? And the only thing I could kind of come up with is it must have something to do with the types of schools that take part in these RCTs. So here you have schools selecting into treatment, or typically we have people selecting into treatment, but here actually they're selecting into an RCT. And so I wonder if the mechanism there is different, or what the effect of that is. And so you could actually kind of probably look backwards. I was saying, right now you're comparing the control to you're matching your comparison to the control. You could kind of tackle this from a generalizability standpoint of tracking the matching instead the control to the comparison, to sort of think about how representative these trials are would be an alternative approach, but also thinking about how that differs compared to observational study context would be helpful. Okay, then I had a couple of slides about, attrition. Okay, so the attrition paper I also found really interesting. It's focused on student level attrition. I know site level attrition is something that occurs in a lot of cluster randomized trials. So I was thinking about, how much these results would apply there. The other thing, though, that I was really struck by was that the attrition bias is that you show is between plus and minus 0.04 standard deviations, which is very close to the guidelines given by Dickey and Chang, where there's this 0.05 guideline, and when the bias might be less than 0.05. And so I was trying to think about your results in comparison to their guidelines, which have to do with both the overall attrition rate and differential attrition rates, and sort of when you're in a safe space and when you're not in a safe space, mostly because I've been doing a lot of work with the What Works Clearinghouse, where we're thinking about methodological guidelines here. So I went back to their paper and I pulled this table, which is what the What Works Clearinghouse, for those who are not involved in the education community, I should maybe clarify. The What Works Clearinghouse is a part of the Institute of Education Sciences, and it's a clearinghouse for causal evidence about what works in education, based upon typically RCTs and high quality QEDs. So this paper has been turned in sort of to the policy there, and I've just sort of noted that there are these guidelines that have to do with overall attrition and differential attrition, and they have these sort of three categories. So I tried to look back at the studies you had and kind of eyeball what you were seeing here, and it looked like you have a lot in the sort of light attrition space, a couple in the medium, and one in the dark attrition, which just made me want to know what, to go back to your analyses. Do you see any sort of difference of the threat of attrition or in those different spaces? Now, given you only have 9 studies, so I realize that this is like getting to subgroups, which are going to be imprecisely estimated. But I think it's important, and it would be really helpful to kind of tease apart the similarity or differences between your approaches. Okay, and then the last thought I had was I was just thinking a lot about the sample and trying really hard to think about, what limitations there might be from this, because I think largely it's awesome that there is data like this that we can look at. And so I was trying to think, so one of them I think is in this first paper is really, as I've said, about the selection into the treatment, versus selection into an RCT. And are those different? Does that make it easier to adjust? Does that make the selection process more knowable? Does that, how is that different? How is that different? I guess I don't have a good answer. The second one is, the second paper, I was really interested in thinking about extreme attrition. So it looks to be like a lot of what you're looking at is not extreme. And given this is a question I have often with the WWC, is like, how often do we see these extreme conditions? But if you look at that graph, for example, I'm always very worried about the fact that we can say that we're safe even when we are up to like 45% attrition in these guidelines. And that seems like an extreme amount of attrition that I'd want to know, are we really safe there? And then the last thoughts I just had were, would the results be different if this were in the US? I don't know. I'm trying to think about the differences between the sort of education systems in the countries and the kinds of interventions being studied. I don't know how that might affect things or not. And then I sort of left with like, does that mean the results here are lower bounds on bias? Are these sort of best case scenarios in some ways because of the kind of data that you have and the kind of selection processes? Or are these worse? Like, should we expect these to be the sort of average case, or are these sort of the sort of lower bound? And so I'm looking forward to hearing, hearing your thoughts. Thank you.
Great, thanks for the nice discussion, Beth. Luke, do you want to respond?
Yes, first, a couple of things. First, thank you for those thoughts. And a lot of them really zero in on a thing that I think is this really interesting question of like, what is big and what is small, and does it matter? And I think we've gone back and forth on it, and usually lands on the answer of it depends. But I think that you pushing on that is entirely the right thing to do. And in particular, and on one hand, the range, going back to the range in the quasi-experimental, is we see a range of negative 0.1 to 0.1. Negative point, like if someone told me that my bias in my observational study was 0.1 effect size units, and I'm in a world where 0.1 effect size units might actually count as like we did it, then clearly that's not great. And on the flip side, if you look at the sort of the standard deviation of all of our estimates, or our estimated amount of variance, that estimate would suggest that in general, like you can get unlucky and end up out there in 0.1, but more often than not, you're okay. And so when the way I've been thinking about, I think I'm just getting sloppier and sloppier as a statistician, possibly, or less and less principled, or I'm not sure what exactly to call it, but I think what it means to me is I look at an observational study now and I go, it's quite possible that this is completely junk, but there's also a reasonable chance. I think this work has made me think that there's a higher chance that an observational study might tell me something interesting than I thought before. I thought before it's like, it's keeping a lot of statisticians in business, but how can you believe any of it? And now I'm like, well, actually, it seems to get it right, or at least mostly right a lot of the time. But again, I think more of this kind of enterprise is needed to really get a handle on it. The other thing I want to say, which isn't in reaction to your comments, but usually I always do this, which is I'll start off and I'll be talking about the statistics and the work, and I'll forget to really showcase my student, Ben, especially now, who happens to be graduating this year and is therefore on the market. This work, I think this work is really excellent. I really enjoyed working with him. He is a fantastic person, and he's just very easy to work with. And so you should all, especially if you're in a position for hiring, make a note of that. And then the other piece.
Can I jump in really fast?
Oh yes, sure, please.
Sure what's allowed, but I think you're right. I think you're pointing to a really interesting distinction. Like as a statistician, we're trained, and we sort of, this is how we think, is to think about worst case scenarios all the time, right? So when I'm talking about, when I look at methods, it's like, well, I don't want to know how it works on average. I want to know what happens in the worst case, and so I'm sort of trying to minimize my largest risk in some way. Yeah. But often empirically, but I find that that's in tension often, even in my conversations in like clearinghouse communities, where people are like, but the data looks most of the time like it's okay. And so you're right, there is sort of a tension in like how you choose an appropriate method. There's a decision framework there, right? That's either, are we trying to minimize the maximum risk, or are we trying to think about the average risk or whatever, that I don't think is often articulated, or even questioned, like, which one is the right way to, should we always be thinking about minimizing maximum risk, or should we often be thinking more about what plausible ranges are and feeling comfortable that this method works 90% of the time? So I just want to say, I think you've raised a really like foundational question there.
Thanks. It's encouraging to hear you say that, because like this is something that has it makes me also think that I should go back and read more of the philosophy of science, of just to remind myself that any kind of learning is not due to one study, but it's really this sequence and different kinds of evidence that triangulate something that's resembling truth. And I hope the social sciences can get there someday, because that's the world I love and live in, and it's a lot muddier than I think the harder sciences, and the harder sciences also have these similar problems. But so yeah, just one last note in reaction to your comments, which is I think the connections to the Whatworks clearinghouse and the Deacon Chang is really interesting, and we should definitely reflect on that too. So thank you for that. And I'll stop there.
All right, great, fantastic. Thank you. So I think now it's time to slowly wrap up. First, thank you so much, Luke, for a very nice talk. Thank you so much, Ben, for rocking Q&A today and answering all these questions. Thanks, Beth, for a very nice discussion. Next time, so next week, there will be no online causal inference seminar. We'll have a winter break. We'll be back shortly at the beginning of January. So we hope that you all stay safe until then and enjoy your winter break. Thank you all for coming, and hope to see you next time.